most modules perform very well. We definitely have outliers that perform quite poorly. Rear of 2,000 hours with poly fingers, and this is the front of TOPCon. So the degradation dynamics significantly slower than the
we also see that anyway, the current standard for UV degradation is not. So we see that we need new reliability testing that goes beyond the standard.
Hello, everyone, and welcome to Sinovoltaics webinar. My name is Rasaya Kaitis. I'm Media Manager at Sinovoltaics, and I will be moderating today's timely webinar on the latest development on UV-ID in TOPCon technology. This webinar comes at a critical moment for the solar industry, as TOPCon technology rapidly scales across commercial and utility projects worldwide. New reliability challenges are emerging, and UV ultraviolet-induced degradation, or UV-ID, is proving to be one of the most pressing among them. Recent research from University of New South Wales has shed new light on exactly how invisible UVB light breaks down silicon-hydrogen bonds in TOPCon cells, leading to measurable voltage losses over time. At the same time, field data from Sinovoltaics is confirming what many asset owners and operators are beginning to feel in their performance numbers. So today we are bringing together two experts on this topic. And before I introduce the two speakers of today, let me share a quick housekeeping rule. So this webinar will last for about an hour, and expert presentations will be followed by a Q&A session. On the right-hand side of your screen, you can see a chat box, so please feel free to share your questions during the presentations, and we will address them at the end of the webinar. This webinar is being recorded and will be uploaded on Sinovoltaics' YouTube channel. If you don't want to miss the newest content updates on YouTube, don't forget to subscribe. So now let me introduce the two stars of today's show. I'm really happy to see again Professor Bram Hooks. Professor, good to see you. I think it's the third or fourth webinar that we are hosting together with Professor.
Yeah.
Professor Bram Hooks is very well known in the renewable energy industry. He's a professor and deputy head of research at University of New South Wales Schools of Photovoltaic and Renewable Energy Engineering. He's also author of more than 300 papers and best known for pioneering the use of aluminium oxide for crystalline silicon surface passivation. Most recently, Professor, your team is providing international leadership on UV-ID in TOPCon solar cells. And you also co-founded P2Agent X, an Australian clean tech company developing AI software and robotics for autonomous solar farm operations. So again, very good to have you back, Professor. And we also have my colleague, Pedro. Pedro, can I invite you on the stage? Yeah, good to see you, Pedro.
Thank you.
So Pedro studied engineering at EPFL, a leading Swiss public research university, and then went on to complete his master's at ETH in Zurich, Swiss Federal Institute of Technology in Zurich, specializing in material science. His research spans the full breadth of photovoltaics technologies, from crystalline silicon and TOPCon to thin film and perovskite solar devices, all developed through hands-on work at the dedicated PV research laboratory. So before I hand over the virtual microphone to Professor Bram, I would like to briefly introduce what Sinovoltaics does for those who are joining Sinovoltaics webinars for the first time. So Sinovoltaics is a global technical advisory firm specializing in solar and energy storage. We help developers, investors, and manufacturers reduce technical risks through due diligence, quality assurance, and safety assessments. We make renewable energy projects safer, more reliable, and bankable. So now, without further ado, I invite Professor Bram to share your slides. And again, please feel free to share all your questions in the chat box.
Yeah, let's see if that's working. I think you should be able to see my slides. So let me start. So today I will, in addition to UV-ID, I will also give an update on our latest insight in corrosion, because yeah, we care very strongly about improving efficiencies at UNSW and many other academic institutions, but there's increasingly focusing on the degradation rate as well, because part of them are important to drive down LCOE, because if you have a very low degradation rate, you can start actually at a lower efficiency to get the same return on investment. If we then look at yeah, like major reliability concerns for like TOPCon and heterojunction, we see that damp heat degradation, although most modules perform very well, we definitely have outliers that perform quite poorly. So 2,000 hours would be, like in a country like Australia in the north, would be 15 years outdoor if this was the only failure mode. But typically, failure modes work in tandem, so it means that these modules would do quite poorly. So, and corrosion, and this is data from PVEL, who produced their module reliability scorecard. They see very similar results as us, that for glass modules, for example, you see degradation coming in at the edges, which is shown here with EL images, electroluminescence images, where bright means good and dark means bad. And you see that the darkness enters from the side, because that's where the water gets in. Of course, the hot topic at the moment is UV-ID, where we see that so PERC, TOPCon, and heterojunction technology all have sensitivities. And for TOPCon, we see outliers which are really scary, with like 10% reduction after UV 120. So that's 120 kilowatt hours of UV, which sounds like a lot, but that's a little over 2 years in Sydney, where I am. So definitely not 25 years. So, and I will get back to that as well. So how do we see it? So we see that actually modules are not uniform. So we see this checkerboard pattern, particularly if you store the modules in the dark. And yeah, the degradation can be quite severe, and we see this dark storage degradation, and I will come back to that as well. So the outline of my talk is that first I will give some updates on corrosion-related degradation. So a little bit of repeat of work that we've presented earlier, but to put it into perspective, and then I will go to UV-induced degradation, and then also see how we can translate this to yield prediction. And I will show you our progress on modeling the main yield stressors like UV and thermal. So first of all, this is work we presented earlier. We published 3 years ago, where we identified new failure modes in heterojunction and TOPCon, but this is the first one, heterojunction, where we see that there's a number of corrosion-related defects that can lead to performance losses up to 50%. So it's really severe. So if we have this type 3 type failure, and I will show the detail later what is the cause of this. And this is after 1,000 hours of damp heat. Then yeah, your PV module performance yeah is too low to really move the needle. Then for TOPCon, we only found 2, but so the major concern was this, again, this type 3 failure, which was a failure over the whole sample. And these are EL images. I forgot to mention that. So dark means bad, bright means good. But yeah, we see that there are failure modes that really lead to very significant reductions. The good thing was that we were able to reproduce all of these failure modes at the cell level. And this is important to repeat this based on our earlier webinar, because this cell level testing is a lot quicker. It's typically 1 day. And we know how we stress the wafer, so that really gives us insight into the failure mode, and we can do a lot of advanced analysis. So we identified that this type 1 failure is contamination. There's various root causes for this, but if you see this in the factory, you can focus on contamination sources. Then soldering flux, and I will go into a lot more detail on how that can cause degradation. And then for heterojunction, we saw that the soldering flux can react with both the paste, so the silver paste, and the TCO, that in this case it was ITO, so Indium tin oxide. And acetic acid in combination with soldering flux leads to this busbar darkening. And that's what we only see when we have EVA modules. The cell level testing can be done very rapidly, which allows us to make rapid progress. And if we then look at particularly flux, we tested TOPCon solar cells in this case. So this work was just published earlier this year. And we took TOPCon solar cells vintage 2019. So that's when TOPCon just started to be entering high volume manufacturing. 2022, when the pace was really picking up. And 2023, just before the introduction of laser-assisted firing, mostly referred to as LECO. And we exposed the cells to two types of soldering flux, so flux A and flux B. These were fluxes that were used widely in the industry. So these were not randomly selected. These were industry-relevant soldering fluxes. And then we exposed the solar cells. So these are not modules. We exposed the solar cells to the soldering fluxes on the front and the rear. And then we did, we first dried it, and then we did cell level temp heat testing. But again, this is relatively quick, as I will show you later. And this was work done directly in collaboration with CSI Solar, but the cells were not made by CSI Solar. So if we then look at the cells from 2019, we see that this axis is performance losses. We actually see that both soldering fluxes are not really able to corrode the cells. So we see even after 122 hours, not really a change in performance. The cells from 2022 were a lot more sensitive, and this is what we've seen consistently in our testing, that the more mature TOPCon became, the more sensitive it became to corrosion before the introduction of laser-assisted firing. So it was a lot worse, but still not as bad as the cells we tested from 2023, where the bars look a little bit lower, but we had to reduce the testing time by a factor of 12, and we had to dial down the temperature by 15 degrees, which is a massive difference. So that's at least a factor of 4, roughly, in terms of degradation rate that we had to tune it down. So these cells were significantly more sensitive. And this is consistent, as mentioned, with other testing that we've seen as well. If we then looked at the cross-sectional T of SEM images and in the top view, we saw that there were some big changes. So there was a lot more metal use in 2019. Of course, we see this reduction in silver usage, so the lines are getting narrower, which increases surface to volume ratio, which makes the cells a bit more sensitive. But what we also saw that the amount of aluminium being used in the cells was increasing. And we saw that resulted that after stress testing, this aluminium was fully reacted, and that resulted in also etching at the interface, and that was the main root cause for this failure. So of course, soldering flux etches all oxides. So if the soldering flux can reach the interface, also all the fricking oxides are gone. So that was quite a big development. So we see that after the introduction of laser-assisted firing, there's still some sensitivity, but it's less, and we will report more on that in coming months. So laser-assisted firing has made life a lot better, but it's not completely solved yet. So the second part is encapsulant-induced degradation, and this is work that we also showed previously. But now we can show you a lot more on the root cause, because we've made a lot of progress there, where we tested various EVA and 3 types of PUE for the TOPCon in glass backsheet modules. So this is module level testing. So of course, most TOPCon modules are glass, and they are glass in part because of this failure mode. But if we then look at so the performance after this 1,000 hours of temp heat testing, we see that one of the bill of materials resulted in a 65% loss. And this paper, which we published in 2024, really created a big stir in the industry that really opened the eyes to many module manufacturers who do not make their own cells. So everybody who is vertically integrated knew that TOPCon cells were very sensitive to certain encapsulants of the metallization. By itself was actually very sensitive. So they were fully aware of this, and this was not shipped in any product. But if you're not aware of this as a module manufacturer, you might be buying cells that have this sensitivity. And if you pick the wrong PUE, your modules will degrade very, very quickly. And this degradation was mainly related to an increase in series resistance. So this was related to the metallization being compromised. So if we look at the EL images, we see that the worst performing, that was PUE-C, that was showing this type 3 failure that I showed earlier. And that's then the failure mode we looked into in a lot more detail. Was yes, the most severe one. There's the second one that was actually, so this is acetic acid. So you can solve that by not using EVA or EPE, it's a lot less. And this again was just contamination, but this is easy to fix. This is also easy to fix. This one, we have to understand the root cause. So if we, the comparison that we show here is that it looks very similar to heterojunction. However, if we look at the root cause, so for heterojunction, we identified that it was mainly related to soldering flux and its strong reaction with TCO. That was the conclusion we came with at that point. But once we tested TOPCon with soldering flux, we did not see the same pattern. So it was not soldering flux by itself. So we speculated that it was an additive of the PUE because it was a uniform failure mode. And if it's uniform degradation, the stress factor has to be available uniformly, and the encapsulant is one of them. The glass would be the other, but the encapsulant was, of course, the main difference in the experiment. So I will not go into detail. You have access to my slides, but there's a lot of additives being used in encapsulants. So they're with various roles. So they promote cross-linking. Some of them even scavenge the acetic acid that forms, so that allows you to use acid-generating encapsulant, and you have UV filters, etc. So your encapsulant is actually not a pure material. With PUE, it's also a class of material. So not every PUE is the same, and even with EVA, there's a lot of additives. And we suspected that one of the additives was the root cause. So we tested for a number of them, and then we tested this PUE of this EVA, where we saw this acetic acid. But we saw that there was not really a lot more additives in there. Then PUE-A, which had quite a good performance, we see a lot of hulls, which is it's a UV-induced degradation stabilizer, so UV-induced degradation of the encapsulant, so not of the cell. But clearly that was not interacting with the TOPCon cell. But then if we looked at the worst performing PUE that had a certain type of UV absorber, and based on the comparative analysis, we identified that was the root cause of the strong degradation. And whoop, that was a bit too quick. We also saw that this this resulted in a cascade of reactions. You can check the details in the paper, and at the end of the presentation, I will provide you a link where you can download all the papers. No paywall. You can read all the details. But yeah, so we identified it was the UVA absorber, and this slide shows a bit more the detail of what is attacking. So this UV absorber actually attacks the main FRIT components, so that's lead and zinc oxide, and also it reacted strongly with the aluminium, which was still present in that paste. So that resulted in the contact degradation. And that's what we often see, that whenever we have a reaction with the metallization, that it's the FRIT components that are being affected, are being corroded. And typically, if the corrosion reaches the interface, that's when we see this strong failure mode. But it also means that initially, for example, the degradation can be eating through your contacts and you would not see anything. It's only when it can reach the interface, that's when you see the degradation. So this could be like a degradation mode that would only pop up after 5-10 years in the field. Then another encapsulant we looked at was magnesium oxide, which is a typical acid scavenger. So if you have EVA, it forms, so when moisture gets in, you get acetic acid. But you can actually include that, and then you can use acid generating encapsulants, and you can actually have better performance. So that's shown here. So just by changing the rear EVA to EVA with the acid scavenger, you see that the loss is a lot less. So it goes from 7% to 1.6. So that's very good. But we saw something interesting when we did a big split in this experiment. So we prepared several mini modules again. So 6 types of mini modules with various types of POE and EVAs and EPE, which is a mixture of EVA and POE. So it also contains EVA. So you would potentially put an acid scavenger in there. And then we again did just normal damp heat testing, 2,000 hours, because it's modules. And then we looked at very detailed characterization. The interesting part was that we saw degradation. So it's 2,000 hours. So the worst bomb was 16%. Of course, these are mini modules. So typically the losses at the mini module level are higher than the large module level. But the main thing we have to look at is that, there's quite a big spread, and some bombs are doing a lot worse. But then the most interesting thing we saw was that there was also significant loss in VOC, so up to 4%. And if we then, 4% doesn't sound like a lot, but if you then look at how much is that in voltage, it goes up to, like, the worst performing case, that's 60 millivolts. So that's of course significant. And that was a 4-cell module, and that was in particular for one type of bomb, white EVA, which had a significant drop in VOC. So we looked a little bit deeper into the EL images again, and there we noticed 2 main takeaways that we see. Indeed, them getting darker. So, and in this case, there was mainly the VOC reduction, but we also saw this interesting pattern appearing. So some parts seem to degrade less than other parts, and this varied a lot cell by cell. So that was what we investigated further. So first thing we did was to look with external quantum efficiency if the performance loss was coming from the front of the cell or the rear. So the fact that the rear looks darker for the degraded cell, and the front actually looks identical to the non-degraded cell, it means that the issue is at the rear, which was very puzzling at first, because for the TOPCon cell, that means you have a degradation of the TOPCon contact, which is buried quite deeply under, so there it has like 100 or 150 nanometers of polysilicon, a silicon nitride film on top of that. So we were really puzzled why we saw like an increase in degradation there. So we investigated, first of all, with time-of-flight SIMS for the cells that had degraded. We've taken them from the module, and we saw significant amounts of magnesium actually in the good and the bad part. So that was puzzling at first as well. So magnesium had reacted because these cells were cleaned. They were taken out of the module, but we've ensured that the cells were clean before we did the measurement. So the magnesium we measured really had reacted with the solar cell. And then if we looked at the cells before, they also did not show any presence of magnesium. So it's like at the detection limit. And then the main difference, so the pattern that we saw was actually due to a difference in allox layer. So aluminum oxide, which is well known to have potential wraparound, particularly if you use ALD, atomic layer deposition, as the manufacturing tool, which is the standard, and try to use back-to-back loading. And we saw that areas with a thicker allox film showed less degradation. They still showed degradation, but it was less than what we saw before. So we postulated, but again, all the details can be found in the paper that is available free of charge on the link provided at the final slide. But then if we looked at cross-sectional TEM, we identified that this magnesium had resulted in a very strong reaction with the silicon nitride layer. And at the end, we came to the conclusion that the magnesium oxide in combination with water actually fully corroded the silicon nitride. And this reaction triggered a degradation of the TOPCon contact. So it's something that's a bit confusing still, why something happening at the surface can really wreak havoc at a polysilicon contact, of a polysilicon oxide contact buried at 100 nanometers. But yeah, we believe it's probably due to the release of hydrogen as part of this reaction chain. So this ammonia, there could be alternative pathways that release a lot of hydrogen, or the fact that there are stress formed. But yeah, details can be found in the paper. But it's quite important to realize that there are some additives that can lead to corrosion of dielectrics, and that can lead to performance degradation. So in addition to interaction with the metallization, no part of the surface is safe for corrosion. And yeah, at the end we tested what was the magnesium content, and yeah, the worst performing EVA had the most magnesium. So there was correlation that we resulted in. That was with the additional measurements we could write that, we could make that causation. So, and of course in products now we use other acid scavengers than magnesium oxide. Then now I'll come back to UV-induced degradation. So a repetition of the earlier slide. It's still a big issue. UV 120, it takes a while to do, but it's still only like 2+ years in a location like Sydney. So from people on the call that are in less sunny locations, like the Netherlands where I used to live, it's a few years longer. But yeah, it's definitely not 25 years. So this is work that we also showed earlier, so that we were able to also for UVID to develop a rapid test that allows us to get feedback a lot quicker using UVB, which is a shorter wavelength UV. It's not triggering a new failure mode, it's just the same failure mode quicker. So we see a difference between fired and unfired. I will not go into detail here, but that will help us to unravel the mechanism. And for TOPCon solar cells without polyfingers, you only see sensitivity on the front, not at the rear. So when we have polyfingers, unfortunately, that will change. So if we then look at what is happening with UV-ID, we see that UV-ID, so UV dose increases recombination. We also saw that in this experiment, we tested thin alox film versus thin for a thick alox film. So we saw that increasing the thickness of alox actually can reduce recombination of UV sensitivity, which is good. So it's one of the mitigation methods. We've developed a few more in the lab, which we'll share at a later time. And we also see, quite importantly, that there is a difference between lightly doped. So this would be the rear of TOPCon with polyfingers, and this is the front of TOPCon with a so boron diffused emitter, where actually the difference between thin and thick is a lot larger. But we see that the overall extent at on an undiffused sample is less, and that's also good news. So even with polyfingers, the rear always sees less light than the front, and it will still be less sensitive. So that's actually good news. So I'm not as worried about polyfingers really escalating the UV-induced degradation. So this is also a repetition from last time, but it's good to show it again. So when we expose to UV, we see this rapid increase. Actually, the worst performing samples, they keep degrading in the dark, and then dark annealing. And this dark annealing was done at 85 degrees, which is not that high in the grand scheme of things. You can actually recover, and you can fully recover if you just anneal long enough. So this allowed us to come to the model that we also presented last time. So that's why I go a little bit quicker. So UV-induced degradation breaks silicon hydrogen bonds. So in the whole dielectric stack, this hydrogen piles up at the interface and creates defects. But also the UV actually increases the fixed charge density in alox. So this is making surface passivation worse. This is making passivation better. But the overall balance is passivation gets worse, so you get higher degradation. In the dark, this high amount of charge that you've pumped during UV exposure goes back, and that is the main result that is causing dark storage. This is completely reversible. I will show you the dynamics in one of the next slides. The recovery that we see, and what we also hope to see in the field, is that the hydrogen that piles up at the interface actually leaks away. It can leak into the bulk. And then your interface is restored. There's still many open questions for UV-ID. So this is one that we published earlier this year, where we showed an interesting correlation between light and elevated temperature-induced degradation. I'm sorry for the bad news. It's not, LTID is still present. It's also present in TOPCon. It's not the dominant defect, but certain process conditions can trigger it. But of course, we know it's present in PERC modules, and we have 1 terawatt of PERC modules fielded. So yeah, it's a relevant topic, and we see that without UV, we see LETID, and with UV exposure, we see no LETID in these samples. So there is a strange interaction which we have to understand in order to really ascertain what the fielded PERC modules will actually show in terms of degradation. So it's a lot more complicated than we thought. So this is great work by NREL. So where they looked at, in this case, the dark storage kinetics per cell, and it's just all over the place, and that's a bit a bit strange because these cells, of course, they're from the same production lines. They're binned to be, so to be roughly identical. They would also be likely produced quite closely together in time. But you see their UV extent is very different, which is still something we don't understand. You see that there's also this dynamics of degradation where even after 500 hours that cell is still degrading. And here we see that UV exposure brings them back to the starting point in 0.2 hours. So that's actually great news. So the degradation dynamics significantly slower than the recovery, which means that, you only have, your night is not 500 hours. And maybe when you're at the Arctic Circle, you will have dark periods that extend for that long. But normally, it's, let's say 12 hours on average. So you would be here. So not really a big issue. And whatever degradation you see, you quickly fix it. And so the good news is that this dark storage degradation is not relevant for field application. Then again, work from Andrel showing the different impact of wavelengths on the performance. So here it's the performance extrapolated in a semi-logarithmic plot in equivalent years in Arizona. So the good news is that like for IBC, PERT, which has the same front as TOPCon, and heterojunction, that IBC in this case was very stable, not always. We definitely seen results in the lab when you take away the front surface field that it's not as stable, but PERT, degradation equivalent years, 30 years it's like a little over 10%. Heterojunction a little bit stronger, but it's overall it's not as bad for these tested samples. But strong wavelength dependence, which we have to further understand. There's also two stages of degradation. So you see first rapid degradation. Details are in the paper. And what we show here is of what Peter shows here is this second phase, which is a bit slower, with skills on a semi-log pace, which means that you really have to look at every doubling. You have an equivalent decrease, but it's so the degradation really slows down in time. So you have rapid degradation at first, and then so the degradation increase, the relative increase from 2 to 4 years is the same as from 10 to 20. So it's a problem that scales quite slowly. But definitely more work is needed, and we have some results in the lab that shows that there's probably another phase after, so recovery phase, in addition to the degradation phase. So hopefully, if that kicks in, this picture would even look better in terms of degradation. If we then look at perovskites, then like perovskite seems to be sensitive to many different stress factors. UVID is one of them. You see that just 100 hours for these cells tested here got you down to 30% of the initial performance, which is not good. Very strong wavelength dependence, very strong temperature dependence, and the scaling, it scales with the square root of the time. So unfortunately, it means it goes a lot. You see the absolute values are a lot, or the absolute decrease is a lot worse, and it also degrades a lot quicker. So for perovskite, there's still a lot of work to be done. So the final part is how can we, really use this work that I showed earlier. So what we do mainly in the lab, how can we translate that to the field? And then it becomes a bit more complicated because even these tests, these great tests that labs like PVAL present, they're typically only one stress factor, but outside the module sees all these stress factors at the same time, and they interact. So they typically, they either can make the impact worse, or they can make it they can mitigate the impact. So PID is a good example that can be mitigated by UV, which is good, but in most cases, they make each other, they really accelerate each other. So in order to do this global scale modeling, it's very important to model these stress factors accurately. And that's actually more complicated than you might think. And this is work we just published I think 2 weeks ago, where we build on previous works that modeled global UV based on satellite data, but we extended that work to include angle dependent and angle and wavelength dependent, because we've seen earlier that wavelength is super important. So we have to model that accurately, and then also the angle dependence is quite important. So there's a big difference what a fixed tilt system sees, for example, versus a single axis tracker. And here you see what's the average daily, average UV intensity a module would see over the whole planet, and we can see it's like an order of magnitude between the worst locations, where Australia is actually one of them. But many locations in Europe are a lot worse. And you also see that fixed tilt, it's a lot less, because you're not following the sun. So it's quite obvious if you think about it, but we've been able to quantify that. And this also means that one test at a certain dose means quite different results depending on the location, and we're helping our partners with that. Then another factor is temperature. So there's very strong temperature dependence from UVID. So it was a little bit in the results presented by Peter Hacke, but we'll definitely be talking more about that in the future. And then if we look at the whole the heat equation for a module, it's quite complicated. So there's of course the solar radiation, then you have radiative cooling, so radiative interaction with the surrounding, then you have convective, so wind cooling. But then also what's often ignored is that electricity is also a way to take out energy, and so the operating conditions of your module affect the temperature. And we've done a lot of developments. So in the load, I will show you one example of that, but also in the radiative cooling, which is in the current models that you would use in PV Syst and a solar farmer, etc. That is not as sophisticated as actually is possible. But the difference in temperatures can be 5 to 10 degrees. In terms of degradation, means a factor of 2. So there's quite a big difference. And one thing we were able to do with our more advanced modeling is to look at different tracking strategies. So if we look at a tracker that is just following the sun versus a tracker strategy that just, if it's curtailed, it actually is curtailing by pointing away from the sun. It can do it in 2 different ways. It can move quicker or move slower than be behind in tracker angle or ahead in tracker angle. And we were then able to study then what's the impact on the heat exchange and then overall the temperature. And we saw that if you control your curtailment or clipping by the tracker, you can actually run your tracker modules even up to 10 degrees cooler, which of course reduces degradation, but also the UV. Of course, if you're not following the sun, you would see less UV. So that's another way to reduce degradation. So to summarize, we've a lot of developments in corrosion. So that's really a lot of things can trigger corrosion. So be aware of this. UV-induced degradation, where I finished, it's still a major concern. We've made good progress, so it's not as bad as it looked like 1 or 2 years ago. But the mechanism is a lot more complicated than we thought at first. So that it will still take years to get the full understanding. But I think in terms of mitigation, like there's already very good mitigation solutions available that bring it down to a reasonable level. And then I'll show you some glimpses in what we do in modeling global scale stress factors that will really help us to assist our degradation modeling. And all the papers from our group, which is probably now the 29 or 29 or 30 in the degradation area, can be downloaded, not using a paywall from this link. Thank you for your attention.
Thanks a lot, Professor. That's really interesting to hear these findings, and we have plenty of questions in the chat box.
Yeah.
I invite Petro to continue on the topic because we also see the quality issues in the TOPCon technology. So Petro will present these in his presentation. Petro,
okay.
The floor is yours. Pedro, I'll also ask you to turn on your microphone.
Yeah, sorry, can you see
Yes,
my presentation? Yeah.
Okay.
So yeah, thank you very much, Raza, for the introduction, and also thank you, Professor Bramhoeks, for the really interesting presentation. So in my case, I'm going to talk about reliability issues and also the emerging risk that calls for need to go beyond what the standard certification testing is available. So as a quick introduction, as we have seen and we know now, the market is currently dominated by TOPCon solar cells. And that means that we shifted from what was previously PERC-dominated market to TOPCon. So we face new reliability issues. For example, LID was previously dominant in PERC, but now that we are facing with TOPCon, as Professor Bramhoeks has mentioned, we are now dealing with new reliability issues, and for example, UV-ID is one of them. If we look at the market, we're also moving towards thinner modules, so that means also new reliability issues that we need to tackle. And the market also shows that in the future, we might be moving from some BOM that are standards to a more climate-specific bill of materials. So maybe that is also a mitigation pathway. Now, if we look at the data that we have from our inspection and different lab reports, here we have 3 different batches of TOPCon modules that were tested, and they were tested following the current standard that we have for UV-related degradation, which is this one. And in this case, it was tested at this dose, which is 60 kilowatt hours per square meter. And as we see in this specific case, only one batch was flagged as a failed test, not because of the standard, which is set as 5% degradation, but because the contract agreement between the client and the manufacturer was stricter, and it was set at 3%. So then it allowed to detect this degradation early on. We also see that anyway, the current standard for UV degradation is not what is actually happening in the field. So even if this dosage and the test conditions is not what happens really in the field, and especially not for 25, 30 years. So as Professor Bramhoeks has mentioned in the previous webinars and today, there's a lot of things to consider when studying UV-induced degradation, and we're still towards understanding really what happens. So I think that research is really essential and the foundation to be able to develop a new UIV standard that can maybe provide accurate testing for the prediction of what is going to happen in the field for 20 to 30 years. We also know from the market that we are dominated by bifacial modules, and that these bifacial modules are also getting thinner and thinner. So that means that even if we are getting towards more efficient structures, we are also facing new degradation mechanism, and especially new mechanical degradation mechanism that can occur maybe during installation or transportation or other parts of the project. So we see that we need new reliability testing that goes beyond the standards, and we need some methods to efficiently detect those defects before these modules are installed. So the solutions we have in our company is we have developed this proprietary algorithm that is called SELMA that allows us to do 100% EL inspection of all of the modules that are in the purchase order, compared to what usually is done, which is a sampling of just a part of the purchase order. So if we look at the numbers on how this has helped us over all of these projects that have been inspected with SELMA, which means more than 40 million modules that have been inspected across 40 different manufacturers. That means that if we consider an average rejection rate of 0.56, it means that 78,000 defective modules were rejected before being installed, so before being on site with hidden defects that might lead to investment losses over time. We also flag here the most common type of defect that this algorithm has shown, which are first solder faults, which are really important to detect early on because then they can induce resistive losses and interconnection that can grow into hotspot, and it could mean a hazard or fire risk. We also have finger breaks that directly translate into instant power loss. And finally, we have also many different types of micro cracks that can propagate when handling these modules. Here are shown also some EL pictures on how our algorithm detects these faults and also how they look like in a typical electroluminescence image. So these, for example, are how solder faults look like in the field. Then we have finger breaks. Here, maybe in the left, is the more clear image on how they look like. And finally, we have different types of microcracks. So they have different naming based on what they look like. So we have maybe single cracks, cross cracks, you can see here, or branch cracks, or many other types of defects. So as a conclusion, now that we advance to more advanced architecture, that means more efficiency, but also more or new sensitivity mechanisms that have to be taken into account. That is why it's really important to do efficient independent audits and also qualification testing. And given that you are bringing into a new AI-driven world, that also means that there's new solutions, like, for example, this proprietary algorithm that we have that can be found to early detect these type of defects. Finally, the advancement and the investment in research on this matter is really important to be able to develop new standards that can actually determine what is the rigorous, proper way of testing the modules to be able to determine what will be the performance on the field. And we also see that the market trend shows that maybe in the future we'll face with another type of cell architectures, which are tandem solar cells, and we will have to adapt to this and maybe find new solutions on how to tackle the new challenges that we'll face. So yeah, thank you everyone for your attention. I think that is it.
Thank you, Pedro. Great presentation, great insights, and we also have questions towards your way. I see Bram joining us for the Q&A session. All right, so let me start with a question for you, Pedro, as you just presented. How does Selma adapt to new cell technologies or materials, especially when they produce different EL signatures?
Yeah, so as we see, now that maybe in the future we are advanced to new type of inherent cell technologies, like for example perovskite, and that will generate a new electrobioluminescence image. But CELMA is continuously being trained with new data that is available, both in the inspection that we do or also from the market. So it's constantly trained to be able to adapt to these new type of changes.
Okay, thank you, Pedro. Question to you, Professor Bram. How much recovery can be done in light soaking post UAD in TOPCon?
Let's see, this question, so light soaking, it depends a lot on temperature. So yeah, I showed you that just by annealing at 85, you could fully recover it. So, and typically the light soaking that I assume the questioner refers to would be illuminated annealing. So yeah, if you wait long enough, you can probably do it completely. If it refers to this initial increase, yeah, that's something you can easily test. It's just a certain amount of UV is needed to bring the fixed charge to the steady state level, and then you're back again. So yeah, so I wasn't completely sure what direction the questioner was asking, but yeah, that's two approaches.
Okay. Another similar question is from ASCO. UV light recovery. What is the required light exposure for heterojunction compared to TOPCon?
Yeah, so heterojunction is it's quite a different mechanism. So with TOPCon, it fully relies on this charge. So the charge that you can inject from the silicon into the airlocks, and then it leaks away very slowly. So with heterojunction, it all has to do with hydrogen mobility. So it would be a lot slower. I would not know out of the top of my head how much slower, but it's definitely a slower process, both in degradation plus in recovery, because it's fully related to hydrogen migration. And we haven't spent as much time on heterojunction. So our intensity is also informed by the market size, and TOPCon is by far the dominant market. But now we devote some attention to heterojunction because we feel that TOPCon is a little bit more under control. So we'll be looking into more detail into heterojunction.
All right, thank you, Professor. Another one for you from Timothy. I understand that many issues are related to the use of backsheets. Does glass-to-glass module configuration really reduces most risks?
Yeah, so this mainly relates to the corrosion, so the corrosion degradation. So for that, yes, glass is the best barrier. So the issue only comes in from the edges. Of course, glass also introduces other, like glass breakage, which is a major reliability concern, particularly in the US, with the severe hailstorms. So I cannot say all risks, but in terms of corrosion, yeah, if you can keep water out of your module for longer, that's good news. Water will eventually get in. You just reduce it. Yeah, if it has to diffuse in all from the edges, yeah, that will take longer. So in that sense, yeah, for many corrosion-related modes, it's the way to go, and that's why most TOPCon modules are glass, and yeah, most, if not all, heterojunction modules. Yeah.
Thank you, Professor. Question from Beryl to you, Pedro. Using CELMA, do you see the percentage of rejections at the factories going down, stable, or going up?
Yeah, I mean, you mean the percentage of the? I guess you mean the percentage of the whole rejections, but of course we're able to detect much more defects, because usually it's only doing a sampling that these type of rejections are done. So of course the percentage will be going up. Yeah.
Thank you. I see that we are already over time, so maybe I'll just take the last question for you, Professor, and then we can wrap up the session. We can follow up on the questions that we are not able to answer via email. So what percentage of module degradation do environment and climate weather events account to?
So if it's relating to extreme weather events, I would not know the exact answer to that. So yeah, of course, if a module, if you keep it keep it outside of keep it inside, and it will not degrade a lot. So I think most of the degradation is because it is exposed to the elements. So extreme weather, of course, that can result in catastrophic failures where a significant part of the power plant is taken out. But yeah, we definitely see that almost all failure modes, like if we look at corrosion, so UV-ID, they scale with the stress factor. So doubling the dose is maybe not doubling the degradation, but degradation will definitely scale. Higher temperatures for most, so the technical term Arrhenius, so energy-driven reactions will double for every 10 degrees hotter. So in a hotter climate, modules will degrade faster, more UV. And if you have the combination, so modes that depend on combination, they will really be accelerated. So definitely acceleration and a big hailstorm we see hill ball sizes up to like 75 millimeters. So that's just hard for any module, and particularly with the reduction in glass thickness that we've seen for glass modules. Not sure if that answers the question.
And maybe another question from Anna, but just rhetorical one. As you mentioned that the modules can recover. So if the recovery for UV-ID is complete after short light soaking, it shouldn't pose a problem in the field, as PV modules will recover fast after sunrise each day. Is that true?
Yeah, it's true related to this dark storage degradation, which was initially reported. So the values were reported after dark storage, and that, of course, that was not representative of what you see in the field. So in the IEC test development, so where I'm also involved, it's ensured that we test quickly enough after light exposure. So the UV degradation that's reported is representative of what you would expect in the field. But unfortunately, it doesn't fully recover. So it's just, it's a degradation you get in the dark. You can fully recover that, but unfortunately, there's degradation because of UV, even without the dark storage generation. And that's what PVAL is reporting, what we are reporting is all, in the recovered state. So after UV exposure, so the numbers would be a lot higher if we would report a dark storage, but that's not relevant. So what the IEC standard will guarantee, I think it's like we have to measure within 4 hours after UV stressing, because then, as I show you, like the degradation is quite slow, and if you measure quickly, then you catch the module at the relevant condition.
Okay, well, thank you.
The work from NREL is very good for that.
Okay, good. And you will be able to share the link with the audience to the research that you were referring to during your presentation. And also we will be sharing the slides of the both speakers with all delegates. I'm aware that we are over time. I want to thank you both, Pedro and Professor Bram Hooks, for really insightful presentations, very technical ones, but translated into human language. I think that's the most important part. So once again, thank you both. And I will welcome you all in the next future Sinovoltaics webinars.
Thank you, Raza.
Bye-bye.
Visit Sinovoltaics.com to learn more.